Hello everyone, I'm Yi Yang. In this video, we are planning to give a presentation of core functionalities of our system. First, Keith will give a presentation of Mastodon pipeline, which is the main data sources that we use to investigate our scenario. And then he will also give an experiment about horizontally dynamic scaling. Then I and SC will give a presentation of YouTube pipeline working and how the data stream coming, etc. This is the pipeline we use to show the platform diversity. Additionally, Zhenghao will give a presentation of CI/CD automation in our project. Every team member followed this standard and developed the individual parts smoothly, which makes our development robust. What's more, I will also give an introduction to machine learning algorithms we use to investigate our scenario, which is Australian major event detection and inference. Roughly, the time series model, autoregressive integrated moving average, and bird topic modeling. Finally, Davian will give a presentation for our front end, focus on the functionality of our model and the visualization. Additionally, in the current framework, Mastodon data is harvested using randomly sampled monthly intervals across a multi-year timeline. While this strategy ensures both temporal coverage, it introduces stochastic variance in post volume across intervals, which in turn affects the stability of residuals in time series forecasting. Despite this dynamic sampling, the topic modeling components remain robust, consistently capture signal associated with major events. For this video, we will focus on the overall effectiveness of our anomaly detection framework, along with its corresponding visualizations on the front end without diving into the detailed modeling internals.
Hi everyone, my name is Keith, and let me walk you through our architecture for harvesting and processing Mastodon posts as shown in this UML deployment diagram. Now, starting from the left, we have our so-called mHarvester fission function, which is triggered for every 10 minutes or so by a fission time trigger. And this function, when invoked, connects to the Australian Internet Observatory endpoint and follows a randomized windowing strategy to fetch Mastodon post IDs. Now, here's what it does in each execution without over-explaining too much. Essentially, the very first thing that this function does is to sample from a random date interval. So essentially, we define a fixed length date interval from 2022 to May 2025. And this date window selection can also be biased or weighted toward a specific year if we wanted to do so. And this could be configured by a config map. For instance, we might bias towards 2024 to overcome cold start issues, like maybe we still have very minimal data in 2024. Now, after a date interval or window has been randomly chosen, this function essentially queries AIO's text search API endpoint for posts containing keywords like Melbourne, Australia, Sydney, Brisbane, basically any keywords that is related to Australia, and retrieves up to 400 post IDs in 2 pagination rounds. And this is another thing with retrieving posts with AIO, because essentially AIO returns posts in pages of 200 post IDs. So in order to keep the fission function ephemeral, we have specified the mHarvester to just retrieve 2 rounds of post IDs for a randomly chosen date window. And each post ID is then validated using a regex pattern to ensure it's a proper Mastodon link, for like ensuring the post is in a valid Mastodon server and etc. And for valid post IDs, it fetches the full post content in JSON format. Once the JSON posts have been harvested and validated, they are sent to an intermediate fission function called enqueue, which publishes the harvested post as a message to the Mastodon Redis topic. Now, the mProcessor function which is the consumer for this Mastodon Redis topic, will be triggered by Keda via a Redis message queue trigger, which again listens to the Mastodon Redis topic. And essentially what this processor is responsible for is it validates the data types and the values from the attribute values in the harvested post, as well as applying sentiment analysis to calculate sentiment scores based on the post body using the Vader algorithm, and summarizes the post using latent semantic analysis or LSA-based text summarization. Then the processed post will be forwarded to a second Redis topic called observations. And there is a consumer function that listens to this observations topic, which is this so-called m@observation functions, which reads the message from observations topic and writes the post to our Elasticsearch index called Mastodon post after checking for duplicates using post IDs. Now, why do we check for duplicates? Because a consequence of this randomization algorithm is that two fission function instances, two harvester instances could sample the same date window. That is not impossible, which means that the retrieve post ID will be exactly the same. Thus, it is very important for us to employ a correct deduplication logic so that we do not ingest duplicated posts inside the index. And once we have post ingested in the Elasticsearch index, if the front end wants to query Mastodon post from the index, it does so via an intermediate fission function called ESQuery, where we have applied a HTTP trigger in ESQuery, so that the front end essentially just makes a GET request to the ESQuery, effectively hitting the RESTful API endpoint of this ESQuery. Now, going back to the randomization, why did we choose a randomized time window sampling? Well, we chose this randomization technique for two key reasons. One, it makes the harvester stateless, meaning we do not need to track which time windows have already been explored, which avoids concurrency issues, since essentially we are working in a distributed setup where these M harvesters could run in parallel. And the second reason is that this random sampling guarantees full coverage of the time windows, thanks to the coupon collectors problem, which is a concept in probability theory that ensures all windows will eventually be hit after enough draws. Additionally, the optional year biasing helps to address cold start issues where uniform sampling might just take too long to accumulate useful data. So we might examine that, for instance, we still have very little post in a certain year, so we might bias the randomization technique to wait such that date intervals falling in 2024 are more likely to get picked. Now, let's see the M harvester function in action. All right, sorry for the hiccup there. Okay, so now that I have walked through the architecture, let me show you what it looks like in real time. So what is this? What you're seeing here is the live function log from one of our Mastodon harvester instances that is currently running in real time. And essentially this log just reports back whether we want to bias the randomization of the date windows or not. And it also logs which date window or interval the algorithm eventually picked. Now you might notice this lines such as first round of pagination skipped, etc. Now this skipping is intentional. It is part of a workaround that we implemented. Originally, AIO's text search API returns results in pages of 200 post IDs, but we noticed that after a few pages, the number of new posts ingested would start to plateau or level off. So rather than processing everything sequentially, which can be redundant, we just manually skip certain pagination rounds to avoid re-ingesting posts we have already likely seen in past harvesters. This keeps each harvester execution lightweight and ephemeral, which is obviously ideal for a vision-based deployment or just any serverless FaaS framework in general. As you can see, we have skipped roughly the first 10 rounds of pagination, and the harvester starts storing posts from the 11th round to the 14th round, which translates to 800 post IDs. And essentially, the rest of the log just states how many posts that the harvester has vetted, because there may be post IDs among the 800 post IDs that may not be valid. Now, I am going to show you a demo of a dynamic scaling and how our architecture supports dynamic scaling. Okay, so what you are seeing here is a real-time sort of log of CADA, which is Kubernetes event-driven autoscaler objects that monitors the queue that bridges between the harvester and processor. So essentially what it does is that once it detects that there is a message in the queue, CADA will automatically deploy the processor instance to take in the message and do its thing. Now, what you're seeing here is that if we look at the first line here, now 200 is just the maximum number of messages in the queue that we allow. And essentially what this first line conveys here is that that CADA detects that there is one message in the queue. Now this is showing 0 because for some reason the metric shown in CADA is off by 1. After the processor instance is launched by CADA, then the message queue will be empty again. But I'm not sure why it shows unknown. But I think this is kind of the initial state of the queue. And once a message is received, then CADA will detect that, oh, okay, there is a message in the queue. There is one message which will trigger, in which CADA will automatically deploy a processor instance. Now here I am trying to do a simple demo that simulates ingestion of Mastodon data, but except I ingest in burst of 7 messages. So I will try to do it. Yeah, so I've tried the demo myself multiple times, and sometimes there is some delay in CADA displaying the latest length of the message queue. Yeah, so I'll just show what the expected result look like once the simulation has been conducted, which is to push a burst of 7 messages into the queue. CADA ideally should have detected that there are 7 messages in the queue. And again, this target matrix is off by 1, in which CADA will deploy 7 additional processor instances to get the message from the queue.
In order to increase the diversity of the data and to demonstrate the scalability of our project, we additionally select the YouTube as another data source. Next, we will demonstrate how the YouTube harvester works. Well, our Y harvester, which triggered by the function timer, will execute periodically according to our configuration. The Y harvester uses a Google API to get the data due to the Google Cloud API limitations. Unlike the Mastodon's free API, we just choose 15 videos about Australia and 5 videos about Melbourne, which published 2 days ago within the same hour to ensure the content fresh but not the immediate content. Then we filter the comments and aggregate the results. Finally, we just send those data to our inquiry by HTTP post for downstream processing or storage.
Okay, after the enqueue function received post from yHarvest, it will send that post into the read this topic YouTube. If there is a message appears in the YouTube topic, the MQ trigger will call its consumer function, which is Y processor, to pick up that message and process that post. If Y process function execute successfully, it will send the message into Y observations topic is the second topic. If its function is execute unsuccessfully, it may send that function message into the arrows topic. Then once again, if the message appears in the Y observations, it will call the second consumer function, which is Y at observations. This function means focus on the writes the post into our one of the index in Elasticsearch. And till here, we store our YouTube posts into Elasticsearch index. Then if a client wants to interact with our Elasticsearch index, he may to use the kubectl port forward method to connect to the feature root. Here is the get method, which will retrieve the data from this function. And the ES query functions, we write our query logic in here to extract the corresponding post. Okay, data stream is coming. Okay, as we can see this screen, the top left, here is our Y harvest, which just harvest 57 posts and put it into our enqueue function here. And then the enqueue function will, just like I said, put the post into corresponding topic. And here is our Y processor function, just process the corresponding comments. Yeah, and it should be just a few moments. It will come to the Y at observation function. Here is the for loop. Yeah, right to our YouTube's index. And let's check the Kibana. Yeah, here is an example just right in the 12 a.m.
Hi, I'm Zheng Hao. In our project, we implement a robust CI/CD pipeline to automate code integration, testing, and deployment, ensuring rapid feedback and high-quality releases. Our testing strategy covers unit, integration, and boundaries, all automatic to catch the defects early and guarantee system stability. Despite challenges with environment differences, we simulate realistic setups in CI to maintain efficiency and reliability. This combined approach helped us deliver reliable software quickly and confidently.
Hello, here is one of machine learning algorithm we use to investigate our scenario, which is detection of major event or anomaly detection. In this part, we first query the data from one of the Elasticsearch index, Mastodon post. And we used roughly 20,000 state training data to train our model. But it's just an example. Of course, I aggregate before training it, I aggregate it in daily granularity, the daily sum. Here, the original data, here is the original data look like. Obviously, there is no clear periodical trend in here, so I don't handle the seasonality explicitly, but it indeed could be an improvement here. Then we used a Riemann model to fit time series, which is so-called series correlation fitting. A Riemann model is the most general version model in time series, except Riemann. The Riemann also takes stochastic seasonality into account. Here, a Riemann model has 3 parameters. The first one is P and D and Q. The P is the auto-regression part, which means the current step prediction, the current step predictions may also depend on the previous steps value. And D is the linear differencing. Means we can somehow make time series more stationary before fitting the model. The Q is order of moving average. So the current prediction of fitted value will also depend on the past fitted value, the residual or error, sorry. Then we use BIC, information selection criteria, to determine the best model. It's a trade-off between model complexity and model fit. The result here is 111, a Riemann 111. After it, we saved our pre-trained Riemann model into the .pkl file. If in the future, if we want to use this model, we just call this file. Finally, I also provide the model with 2 95% confidence interval, upper bound and lower bound, which can be treated as criteria to determine the anomaly date. The calculation is pretty straightforward. You can look here. It's just model, our model, fitted value is our model, plus or minus 1.96, which is under the normality assumption, the corresponding z-score of 95 bound. Then times the residual series standard deviation. Hello, here is the second part of machine learning algorithm we use to investigate our scenario. Topic modeling. Here, I plan to talk about how we trained topic model. The first, we perform text cleaning. In the first step, we transform all the text in all the string into lowercase. And then we try to remove URLs, HTMLs, markdowns, emojis, special characters, and the stopwords. After doing that, we can get a clean text. So the clean text was further treated as inputs into the sentence transform here. Then the sentence transform will provide us an embedding vector, which is lives in a very high dimensional Euclidean space 384. Since the distance-based clustering methods suffers from curse of dimensionality, which motivates us to perform some dimension reduction method first, and then to perform the clustering algorithm. Here, we consider use PCA dimension reduction technique. We roughly can get 84% variance explained by first 150 PCs, which is not bad result. Since it's in the meantime, we can achieve roughly 2/3 dimension reduction from original one. Here is the evidence we can achieve like 84% PC variance explained. Then we forward our reduced embedding vector into k-means algorithm. We use album method to select optimal k. Here, the optimal k is 11. And we extract clustering labels here for visualization. For the visualization, we performed one more PCA to reduce dimension to 3 dimension and 2 dimension. Here is the visualization. Of course, the visualization in here, lack of physical meaning, indeed. So it's not our end goal in topic modeling. So in the next step, we will try to forward the clustering label as to the topic modeling, which can be the clustering label can be treated as a soft label or pseudo label to train our topic modeling. Here, we forward the clustering label here, and here is an example of what's the topic provided by topic modeling look like. And here is a visualization. Let's check the topic 2. It's train rail, which is a transportation of corresponding related to the Australia or Melbourne. The 3, yeah, it's a police, Melbourne man protest news. It's corresponding to the law or some police related.
Okay, thank you everyone for the previous delivery. Now I will walk you through the front-end component of our system. As previously mentioned, our project's core objective is to combine time series forecasting and NLP-driven topic modeling to monitor sentiment dynamics in social media. This enables early detection of trends, risks, and public reactions, offering practical applications in areas such as crisis response, trend analysis, and real-time public discourse monitoring. The system logic is modularized into 3 core utility files, each responsible for a distinct functional domain. First, the I/O utils. This module handles all I/O operations and backend integration. It provides paginated and REST-compliant queries to the efficient backend Elasticsearch service. It supports both time series and NLP modules in the sense of the definition of load NLP data frame and load time series data frame. Next, the NLP module encapsulates all natural language processing logic, including a text cleaning and normalization, sentence embedding using sentence transformer, and topic modeling via a topic model. It supports both local model inference and online embedding workflows, allowing flexible deployment across environments. And lastly, the visualization util. Core visual components related to topic module are encapsulated in this utility. This module leverages the Matplotlib, Seaborn, and IPY widgets to deliver a responsive interactive analysis experience within the notebook interface. Now let's take a closer look at how it works. First, user need to set the time window. Time window can be chosen at the user's preference. And once they click the set window button, they receive the message saying that time window was set successfully. Then user can set the forecasting length and choose a preferred model. The model can be replaced or added to the drop-down list manually. Also by clicking on the run analysis, and we're ready to go. The forecasting table gives the forecasting sentiment score from the last existing post date. The time step will be set as previously showed. And the visualization illustrates the performance of an ARMA 111 model fitted to daily sentiment scores over the year of the choosing time window. By such visualizations, it is reasonable to noticing some like CI bypassing behavior through the given time window. From this point, we decide to do some anomaly detections on a date basis from this time series analysis. So we basically record the anomaly occurrence date and send them into a CSV file and later used for the topic modeling analysis. And these are the REST functionalities for the time series demonstration, which will be explained in detail on the presentation. Okay, we're all good to go with the NLP model. So for the NLP model, let me go through it. There we go. So as the NLP model has some like relatively slow loading time, we decide to demonstrate this functionality through a pre-run model. But later, we can also demonstrate how it actually works in a dynamic way. So first, let's come back to this model. The model actually enables real-time exploration of emerging topics and sentiment anomalies from social media data. This module is also designed as widget-driven interface within our Jupyter environment, empowering analysts to configure and run natural language analysis pipelines with minimal coding overhead. Well, relatively minimal overhead. It includes control to select a preferred embedding model. One can adjust the k-means cluster for topic granularity. And one can use local CSV on their preference, similar as before. And we can use either to do a local pre-trained per topic models for faster inference. And lastly, one can choose the batch size as well as the device to acquire some faster inference behavior. And then, as one tick on the run analysis button, you can see from as the inference is proceeding, we deliver such message. There are basically several visualizations we demonstrate from the visualization files. So we can basically check the top topics by document count. This gives the user an overall ideas on the topic training on a document basis. And next, we can find the happiest and saddest topics by its corresponding sentimental score. And the stacked positive negative sentiment demonstrate how these topics varies as time series and its corresponding anomaly occurrence. And lastly, we do this global timeline with anomalies visualization for better understanding of anomaly detection. One important thing that we are interested in, as mentioned before, that we actually more interested on this topic distribution on anomaly dates with example posts. Upon selecting a specific anomaly date here, for example, if we can choose on this day, June 25th, 2023, the system renders a bar chart showing topic distribution on that day, alongside markdown formatted previews of representative posts per topic. This provides a qualitative interpretability by allowing an analyst to drill down into what people were actually saying and which topic dominated the discourse during a sentiment anomaly. We usually ignore the -1 clusters is basically this sort of cluster stands for the noise. But one can see that the geocaching topic is actually dominates the other topics on this day. And this geocaching is related to our Australian-wide activity that happens within the nation. Together, the module closes the loop between numeric time series anomalies and semantic drivers in the underlying discourse. It allows for moderate, flexible, explainable insight into social media dynamic, critical for applications such as event detection, public risk monitoring, or narrative trend analysis. And that is all for the front end. Thanks for watching, guys.